continue looking through the factors that affect the rates of SN1 and SN2 nucleophilic alkyl substitution reactions, we want to move on to solvent effects, which is perhaps the most complicated. And we're going to divide those solvents into three classes. And those three classes of solvents are Protic solvents, all Protic solvents are polar because they all contain atoms that are capable of hydrogen bonding. Which means that they're all going to have either an HF, an HO, or an HN bond present. Obviously, there's only one compound that can have an HF bond, and that is hydrofluoric acid itself. Liquid hydrofluoric acid is not a solvent you want to be running in. It dissolves glass, so we'd have to be running platinum vessels, and it's quite dangerous. So really, that's kind of a moot point, but we're talking about things with OH or NH bonds. So we're talking about alcohols and amines, and importantly, water. Not that many organic reactions are run in water, but a lot of organic reactions are run in a mixture of water and some other water-miscible solvent. So we're talking about water, we're talking about alcohols like methanol and ethanol, and we're talking about liquid ammonia, which has a boiling point of -33 degrees C. So you can actually run reactions in liquid ammonia fairly readily. And we're talking about amines, things like triethylamine and, well, not triethylamine because it wouldn't have hydrogen bonding, but diethylamine, for example, diisopropylamine. Diisopropylamine is actually a fairly common solvent. And we're talking about things like olivine, things that are capable of hydrogen bonding. Protic solvent, because of the proton that's attached to the nitrogen or the oxygen in this case. So that's the first class. Second class of compounds of solvents that we're going to be interested in are the polar aprotic solvents. And polar aprotic solvents have a polar pi bond in them. So we're talking about things like acetone, and acetonitrile, which are carbon compounds, but then we're also talking about some things that have phosphorus and sulfur in them as well. This compound is dimethylformamide, N-dimethylformamide. Which is abbreviated DMF. And then two other important polar aprotic solvents are dimethyl sulfoxide, abbreviated DMSO, and hexamethylphosphoramide. Which is abbreviated HMPA, dimethylamino groups attached to the phosphorus. So in all cases, we have a polar pi bond. Protic solvents, because they have a small electronegative atom with a lone pair, and they have a hydrogen attached to that small electronegative atom, solvate both cations and anions effectively. Polar aprotic solvents have a partially negative atom with a lone pair on it. Very effective, therefore, at solvating cations. In all of these cases, particularly in the case of hexamethylphosphoramide, you've got very sterically bulky groups attached to the partial positive end of your dipole, which means that the anion has trouble getting to the partial positive and is therefore not solvated very well. And that's a crucial difference, because the nucleophile in nucleophilic alkyl substitution reactions is an anion. So the polar aprotic solvents do not effectively solvate the nucleophile. And as it turns out, that is going to raise the energy of the nucleophile and speed up an SN2 reaction. Whereas the polar protic solvent solvates a solvent like water or an alcohol, actually formed a double solvent shell. That dramatically lowers the energy of the nucleophile and slows down the reaction. So we will find the polar protic solvents. There's no such thing as a non-polar protic solvent, right? All protic solvents are polar. Polar protic solvents slow down SN2 reactions, whereas polar aprotic solvents speed up SN2 reactions. So by changing the solvent, we can change the rate of the nucleophilic alkyl substitution reaction, and therefore change whether the reaction is more likely to go by an SN2 pathway or by an SN1 pathway, because polar protic solvents will speed up the SN1 reaction at the same time as they're slowing down the SN2 reaction. The third class of solvents are the non-polar solvents. And those are things like hydrocarbons and halogenated hydrocarbons. And aromatic hydrocarbons. And ethers. So we'll have things like hexane and dichloromethane. And benzene. Those don't really dramatically affect the rate of the SN2 reaction because they solvate neither cations nor anions, which means that they're really probably not going to be effective solvents for nucleophilic substitution mechanisms anyway, because the salt that is forming, that is the source of the nucleophile, sodium cyanide, for example, is not very soluble in these nonpolar solvents to begin with. So we're not really going to worry about the nonpolar. Actually, the protic solvents and the polar aprotic solvents change the rate of reaction. So something that's important to think about, let me restate that, one has to know the mechanism of the reaction, because in order to determine whether the reaction rate is going to be increased or decreased by the presence of the solvent, we have to consider what the solvent is going to do to the energy of the starting material and to the product and to the transition state of the rate determining step. In the case of the SN2 reaction, that's the only step. In the case of the SN1 reaction, that's the first step, where the leaving group spontaneously just departs, leaving a carbocation intermediate. Both the Protic solvents and the polar aprotic solvents have a greater effect on ions than they do on neutral compounds. And that probably makes sense because the ion, as a charged species, is a higher energy material than a neutral molecule in the first place. So regardless of whether it's protic or polar aprotic, this is true. Solvents are going to have a larger effect on the ion energy than on the energy of the neutral molecules. In the SN2 reaction, the ion that matters is an anion. It's the nucleophile is in the starting material. Therefore, the solvent has a larger effect on the energy of the starting material than on the energy of the transition state. Because the transition state has only partial charges, whereas the nucleophile in the starting material has a full negative charge. In an SN1 reaction, on the other hand, the energy of the nucleophile is not relevant because the nucleophile is not part of the rate determining step. And the ions are in the intermediate. Energy of the intermediate than on the energy of the starting material. Because the rate determining step has a late transition state, it will also have a larger effect on the energy of the transition state than on the starting material because, and in this case, the product is the carbocation intermediate. So the transition state looks like the carbocation intermediate. Since the solvents have their largest effect on the things that are ions, in this case the carbocation and the leaving group has anion, there's going to be a larger effect on the transition state energy than on the starting material. Which is the opposite of what we observed with the SN2 reaction, whereas the SN2 reaction, we have a larger effect of the solvent on the starting material energy than on the transition state energy. In the SN1 reaction, we have a larger effect of the solvent on the transition state energy than we do on the starting material energy. And what we want to do to determine whether the reaction is going to be sped up or slowed down is we want to compare the energy gap between the starting material and the transition, where it would be in a non-polar solvent, to the case where it's interacting with either a protic solvent or a polar aprotic solvent. So we need to start, in both cases, by writing the mechanism. And then what we need to do is think about how the solvent is going to interact with the various species that are in that mechanism. So let's look at the SN2 reaction first. And we'll use a very simple example. We'll use iodine-methane. So that we're working with relatively small number of atoms. Iodine-methane is a liquid. It's a very good methylating agent. There's no steric hindrance. So we know that SN1 reactions are not possible. This is going to have to go by an SN2 reaction. And let's use as our nucleophile sodium azide. So our nucleophile is the N3- ion. That looks like this. And the mechanism is going to involve the N3- ion attacking the carbon and pushing out a leaving group. And that's a concerted reaction. So we're going to have a bond starting to form to that N nitrogen. And we're going to have a bond to the iodine breaking. And the partial negative charge on each of those and the carbon has gone into roughly a trigonal bipyramidal geometry. And when we're done, we have the corresponding azide. But that's not really that important, because we're not really concerned with the energy of the azide, since that's not going to affect the rate of the reaction. So we can put this on an energy diagram. And we can see that we have our starting material, we have our high energy transition state, and then our product. And this reaction is going to be exothermic because the carbon-nitrogen bond is much stronger than the carbon-iodine bond. And we've got an activation energy for this hypothetical unsolvated case in white. Corresponding to the gap between the starting material energy and the transition state energy. So what we want to see is what's going to happen to the energy when we put this in a protic solvent. And let's choose methanol. simplest alcohol as our Protic solvent. So what's going to happen to the azide ion when it's surrounded by methanol? And I'm going to erase the product because the product is not relevant to our discussion. So we have our azide ion. It has two formally charged minus nitrogens, one on each end, symmetrical, a positively charged nitrogen in the middle. And if we surround that with methanol, we would expect that methanol will cluster around the ends where the nitrogens are negative. The hydrogens interacting with the negatively charged nitrogen. And then we would also expect that we might get some solvation from the oxygens of the methanol with the positively formally charged nitrogen in the middle. So we formed a solvent shell around our azide ion, and that should be a relatively strong solvent shell because nitrogen is a small atom and hydrogen is a small atom, and so we can get a quite short distance between the nitrogen with the negative charge on it and the hydrogen. So this will be strongly solvated. Of the azide ion. So if we were to put this on the same energy diagram that we're working with here, we would expect a significantly lower energy forming with the azide ion. And now what we need to do is consider what this transition state will look like when it's surrounded by methanol. So in our transition state, we have an iodide ion. We have our iodide ion with a partial negative charge on it. It's got some lone pairs on there, but it's rather large. And because we only have a partial minus charge on the iodine, the interaction is not going to be as strong either. So that's not really going to change the energy very much at all. On the other end, we have our azide ion, which now has a partial negative charge on it. And because it has a partial minus charge on it, it will still interact with methanol. Obviously, the one on the end will continue, right, because it still has a partial minus charge on it. But this is going to be a weaker solvent shell. Because Coulomb's law tells us Coulomb's law is the most important law for organic chemistry, really, well, for chemistry in general. Coulomb's law is very important. That if we have a partial minus charge on there, we decrease this, that decreases the force of attraction. And if we increase the distance, as we have here, because iodine is so much larger than nitrogen, and it has a partial minus charge, we're going to decrease the force of attraction. The solvent shell is much weaker. Because the solvent shell is much weaker, it's going to lower the energy, but it's not going to lower the energy by as much as it lowered the energy of the starting material. So we will have a lower energy transition state. That's going to drop a little bit. And the product, right, since it's iodide, will be largely unaffected because the iodide doesn't need to be solvated in order to be stable. And then we can show in yellow here, dotted yellow line, what the activation energy now looks like in the solvated case. And I think you can see that that is a longer vector than that, than it was in the unsolvated case or the non-polar solvent. And because we know from the Arrhenius equation that the rate constant is equal to RT, if we increase the activation energy, we're going to decrease the rate constant. And therefore, the rate is going to decrease. So the SN2 reaction in a Protic solvent is reduced. It's slowed down. So what about the rate of the SN1 reaction in a Protic solvent? And we'll stick with methanol. And for the SN1 reaction, let's look at tertiary butyl bromide or 2-bromo-2-methyl propyl bromide. And we'll have an equilibrium reaction where the transition state has a partial bond to bromine, building up a partial negative charge on bromine and a partial positive charge on carbon, stabilized by hyperconjugation. And then when we're done, we'll have a planar carbon-cation intermediate and bromide ion. And this is the rate determining step. And if we put this on an energy diagram, we expect to have a significantly endothermic reaction, and we expect it to have a late transition state, where the transition state looks a lot like the carbocation intermediate. Once again in white, we have the unsolvated case. What happens when we put a solvent in? Well, very little to the starting material. The starting material does have a polar bond in there, but there's not going to be a lot of solvent interaction with just those partial minus, partial plus charges. It will actually stabilize it a little bit, but the difference in energy at the starting material would be expected to be quite small. Once we have the carbocation intermediate, we would expect that carbocation intermediate to interact readily with the methanol. In fact, we know that it interacts strongly enough with the methanol that in the absence of will actually react and we'll end up making an ether. We would also expect the bromine to be surrounded by solvent, bromide, sorry. So we're going to form a solvent shell around both the positively charged carbon and the negatively charged bromide leaving group. That's going to lower the energy of the carbocation intermediate. And it's going to lower the energy of the carbocation intermediate by substantially more than it lowered the energy of the starting material. Methanol will also surround the partial negative charge on bromine in the intermediate, not quite as strongly, but we know this is a pretty late transition state. So there's actually a significant negative charge on the bromine by the time it reaches the transition state because it's late, and a significant positive charge on the carbon. So we're going to be solvating our transition state pretty well as well. Not as strongly as we solvate the intermediate, but much more strongly than we solvate the starting material. So we're going to lower the energy of the transition and how much we lower the energy of the starting material. And then when we connect this, what we want to do is compare the activation energy that we see in the unsolvated case to the activation energy that we see in the solvated case. And I think you can see that the white arrow, the unsolvated case, is larger than the yellow arrow. So our activation energy in methanol is actually smaller than the activation energy in the absence of solvent or in a non-polar solvent. If that's true, then the larger activation energy for the unsolvated case will be associated with the smaller rate constant. So K in methanol is going to be greater than K unsolvated. And the SN1 rate is increased by the presence of the Protic solvent. Which is exactly the opposite of what we saw for the SN2 reaction. Because in the SN2 reaction, the energy of the starting material was dropped by more than the energy of the transition state, which meant that the solvated arrow would be larger. So in a Protic solvent, we will decrease the rate of the SN2 reaction and increase the rate of the SN1 reaction, and that will have the overall effect of, in some cases, switching the major mechanistic pathway from SN2